such that AB equals 0, so that if A is invertible, then B equals 0?
Yes.
Are we proving that, like, generally?
Yes.
Today?
Yes.
Okay. And how do we show that A is invertible? Is it like...
Oh, you're assuming it is.
Okay.
It says if it's AB is 0 and if A is invertible. So you assume both those things.
Mm-hmm.
So if you start with AB equals 0, what would you need to do to get to B equals 0?
Would A have to be 0?
Well, you know it's invertible, so it can't be 0.
Does it have to be an identity?
It doesn't have to be an identity. But what do you know about A? If it's invertible, what exists? What does it mean to be invertible?
That it can, like,
Thank you.
do the other way?
Say that again.
Like, can it, like, switch? Because it's a square?
So it's a square matrix. But what is it in general? What does it mean for a matrix to be invertible, or even a number to be invertible? What does it mean?
You can take the inverse of it?
Okay. And so, what is it? What does the inverse mean then? What do you use the inverse for?
To get something back to its original?
That would be the original back to the what? So, for example, if you're trying to solve the equation 3x equals 9, what do you need to do?
Multiply by 1/3.
Multiply by 1/3. That's the inverse, right? Why do you multiply by 1/3?
To get x by itself?
Okay, it's good because what happens when you multiply by 1/3?
That equals 0.
It becomes
1.
1, right? So you multiply by the inverse, so you get the identity.
Okay.
Okay. So if you've got AB equals 0, and you're trying to get to B equals 0, what do you want to do on both sides?
Multiply by the inverse of that.
There you go. Yeah. That's the idea. That's what you want to do.
How was your weekend?
That was all right.
Did you do anything exciting?
I read math questions to junior high kids. Math counts was on campus this weekend, so on Saturday. So they have what they call a countdown round, where they go head to head and answer math questions. So I was reading those.
That's
like grade school things?
They're middle school.
Is it a competition?
Is it?
It's a competition. Who won?
The team that won was Rural Forsyth. Student who won, I think, was from Mount Sinai, if I remember correctly, but the team was from Rural Forsyth who won, I believe.
And they do that here on campus?
They do that, the regional ones here on campus, and the winners get to go to state, which is in Joliet.
So they're kind of like scholastic type thing?
Yeah, but it's all math. It's at the end of it's kind of like Scholastic Bowl. The beginning of it, they actually do written tests. They do some individual tests, and then they do team competition as well. So, and then whoever does well at state will go to nationals. The national competition has actually been on ESPN2 before. For several years since I saw it on ESPN2. It was kind of funny. Had color commentary and everything. They had somebody in there talking about how somebody could solve it so fast and talk about what it. It was kind of funny. I found it amusing. So yeah, I did that on Saturday. I like it. It's good to see the young kids doing math. At least I think it is. Other questions at all? All right. Well, let's talk a little bit about finding inverses of matrices. So let's look at. What's my sheet there? There it is. So I want to look at, this is number 7, part B, on page 58. And the matrix they have is -1, 3, -4, 2, 4, 1, -4, 2, -9. And the problem asks you to find the inverse if possible, or so the idea behind this is to do what we talked about right at the end of last time. We did basically we did proofs all last time, but the idea for that last proof was what we need to do here. So you have a matrix. You want to basically undo this matrix, get it back to the identity, right? And the way we're going to do that is through elementary row operations until we get to the identity or get to a point where we get a row of zeros. Okay. Because if we get to a point where we have a row of zeros, we know that we can't be invertible, because if you take a matrix with a row of zeros in it and multiply it by anything, you're always going to, or on the left by anything, sorry, multiply it on the right. Try that again. If you have a matrix with a row of zeros and you take another matrix on the right and multiply, the answer will always have a row of zeros in it, so you can't get to the identity. That was where I was trying to go with that and misspoke twice. All right, so we're going to do elementary row operations on this. Either we'll get to the identity matrix, or we'll get to something that has a row of zeros and we'll know that it's not invertible. Right? The reason why we're going to do elementary row operations on that is because we know that elementary row operations can be realized through matrix multiplication, through those elementary matrices, right? So the idea is that if I have a matrix A, and I multiply on the left by a bunch of elementary matrices and get the identity matrix, what does this product have to be? A inverse, right? Okay, so this part, when I'm done, has to be A inverse. And again, the idea behind that is that if it acts like the inverse of the matrix, it has to be the inverse of the matrix. Right? So the whole idea of this is to be able to keep track of your elementary row operations one after the other so that you can get to the inverse. Well, the idea behind this, of course, is that if I put the identity matrix on the right here, when I augment, if I think about multiplying all of these together on the left for this matrix to do the row operations, if I put an identity matrix augmented on the right here, it'll multiply that each of those elementary matrices by the identity matrix, and basically on the right, you'll end up with that product. What I mean is that if I take my matrix A and augment the identity matrix, doesn't matter what the, it really doesn't matter that there's the identity matrix here for what I'm going to say here in a second, but if I augment the identity matrix and then you multiply on the left by whatever, but when we do the multiplication, remember we line up rows to columns, right? Right? So when we do row to column, notice that I can think about almost a distribution property here, that this will just be this matrix times A, and then this matrix times I, but that matrix times I just gives you the matrix back again. Right? Because again, all we're doing here is, all this is saying is that to get this left side, I'm taking each of these rows times each of those columns, right? It doesn't affect this on the right at all. To get the right side, I'm getting each of these rows times each of these columns. It doesn't affect the left side at all. They call this block multiplication, by the way, because you're just dividing your matrix. And you can do this by rows and by columns, as long as you have the same sizes match up. You can do these in chunks, because again, you're just matching rows to columns. It's not mixing columns, right? You have a fixed row, a fixed column at any given point. All right, so then again, you can see why if I take each of these other row operations and start putting them on the left here, they're going to get added in here. So then what you'll end up with on that right-hand side is the inverse. Oh, hush. Okay. All right, so the matrix again was -1, 3, -4, 2, 4, 1, -4, 2, -9. And you want to augment the identity matrix. And now we're going to go through the row reduction process just like we did before. What's the first step that you want to do if you're trying to row reduce this? Put this in reduced row echelon form. What's the first step?
Do you want to do like the first column and get the first one and then the zeros below it?
Exactly. I want to get a 1 up here in the upper left-hand corner and get zeros below it. What do I need to do to get a 1 in the upper left-hand corner?
-1.
It's probably the easiest way to do it, right? Do -1 times row 1, replace row 1. Doesn't change row 2. Doesn't change row 3. And all it does is flip the signs for the first row. Is that okay? All right, so now we want to get zeros below it, like Megan said. What do we need to do to get zeros in the second row and the third row in column 1? What do we need to do?
Multiply the first row by negative, or just the negative and then.
Okay, so then multiply the first row by -2 and then add it to row 2. And working off the same row, do what to get rid of the -4?
What, 4 times row 1?
Good, 4 times row 1 added to row 3 and replace row 3. That doesn't change row 1 at all, but it does change the other 2 rows. First entry is a 0. -2 times -3 is 6 plus 4 gives me 10. -2 times 4 is -8 plus 1 gives me -7. -2 times -1 gives me 2, and added to 0 gives me 2, and the last 2 terms are the same. Last 2 entries are the same. All right, so now do 4 times row 1 added to row 3. 4 times 1 plus the -4 is 0. 4 times -3 is -12 plus 2 gives me -10. 4 times 4 is 16, minus 9 is 7. 4 times -1 is -4. Add that down and just get -4, and then the other 2 don't change because they're still zeros.
Does the 1 not change? Oh, never mind.
Okay, I'll never mind. I can do that. I can do that. And again, you can use your calculator if you want to use those for the row operations, but don't just type in the matrix and then do reduced row echelon form, and definitely don't just type in the matrix and hit A inverse, which you can do and it'll give you the right answer. It's just, I want to see that you know how to do the process. Okay? I'm well aware the calculator can do it. I want to know if you can do it. Okay? All right. Hopefully, well, at this point, you would want to try to get a 1 in the second row, second column, right? Get that pivot in the second column, and then get zeros above and below. But at this point, you probably recognize something bad is going to happen. If I look at the second and third row, all right? If I just add the second and third rows together, what am I going to get at the bottom? I'm going to get zeros, right? If you just do, without even worrying about getting a 1, if I do row 2 and add it to row 3 and replace row 3, you'll get 0, 0, 0 there, right? And then the other parts are what? -2, 1, 1. Doesn't really matter, but that's what you get, isn't it? So when you try to put this in reduced, well, when you put this in reduced row echelon form, are you going to get the identity matrix here? No. What we've shown here is that your original matrix is what's called row equivalent to a matrix of a row of zeros. Okay? So the matrix, the original matrix, is row equivalent to a matrix with a row of zeros. All row equivalent means is that there is a sequence of row operations that change one matrix to the other. That's all row equivalent means. And if you've had discrete math, you would have talked about equivalence relations. Yeah, me for discrete math. I know you talked about equivalence relations, but you talk about equivalence relations. Row equivalency is an equivalence relation for matrices. Yeah, Megan.
Could we go over like the steps of like which order you should be trying to do things in order to get a matrix to?
So the way I would do, I did this one a little bit different because we noticed that the rows were the same, right? Essentially.
Yeah.
But what I would do always, if you're going to get to the identity matrix or whatever, I would always get a 1 up here, get zeros below it.
Mm-hmm.
Go to the next column over, get a 1, get zeros above and below it.
Mm-hmm.
Go to the next one over, and just repeat that process until you run on the steps.
Okay, so you should be doing the ones first and then the zeros.
That's what I would always do, the ones first and then the zeros. That's how I would do it, especially if you're doing it on your calculator anyway, because then the fractions will mess you up. The hardest part about doing those by hand is when you get a bunch of fractions in there. And if you're using the calculator, then it won't be so bad. All right, so since it's row equivalent to a row of zeros, a matrix of the row of zeros, this means the reduced row echelon form, I'll just write it as RREF because I'm lazy, of the matrix is not the identity matrix. Because an identity matrix doesn't have a row of zeros in it, right? So that tells us that the original matrix is not invertible. Remember yesterday. Remember on Friday, we may have talked about it yesterday, but not with me. But remember on Friday that we said that we gave that list of 6 things that were all equivalent? One of the things that's equivalent to being invertible is being that the reduced row echelon form is the identity. Well, if you go through the row reduction and you hit a row of zeros, you can't get the identity matrix. It's not possible. Right? I can't magically create a 1 from a 0 here, right? I could get a 1 here, but then there would be something non-zero here. Right? I can't get a 1 here without messing these zeros up, is what I'm saying. Okay? So, if you get to the point where you get a row of zeros, when you're row reducing, and the matrix isn't invertible and you're done, and you go on to the next problem. Okay. Now, let's see if we've got one that is invertible. Try one here. Let's do, why not 8a? It has some fractions in it, but that's okay. Because the first thing I want to do is just get rid of the fractions. So 8a on page 58 has 1/5, 1/5, negative 2/5, 1/5, 1/5, 1/10, and 1/5, negative 4/5, 1/10. All right, so again, what do we do with the matrix? What's the first thing we do? Okay, so we want to get a 1 in the top left-hand corner. What do we augment over here on the right? Identity matrix. To get a 1 on the upper left-hand corner, what do we need to do? Multiply by 5. And just to make everything else easy, so I don't have to deal with all the fractions, I'm going to go ahead and multiply the second 2 rows here by 10 each time, just so that I can get rid of the fractions. Only because I don't really want to deal with the fractions. So I'm going to do 10 times row 2, replace row 2, and 10 times row 3, replace row 3.
Those are valid row operations. So there's nothing wrong with doing that to help you out. So the second row becomes 2, 2, 1, 0, 10, 0. And we get 2, negative 8, 1, 0, 0, 10. I did my arithmetic correctly. This is why I was encouraging you to do the row operations on your calculator. When doing these problems, one of the more common errors that I'll see is forgetting to do the stuff over here. You remember to do this part, and then you get into that vertical bar and forget to do this part. So, one of the reasons why I'm encouraging you to use the row operations in your calculator so that it'll spit out the matrix that you need. The individual row operations, right? Not hit reduce row echelon form will be done. Okay. All right, so now we want to get what? We've got that 1 in the upper left-hand corner. What's the next step?
Get zeros below it.
Okay, and to get zeros below it, what do we need to do?
Multiply row 1 by -2 and add it to row 2.
Okay. Okay. That does not change row 1, so I'm just going to recopy it. If we do that in row 2, the first two numbers are 0, aren't they? And the next one is 5, and negative 10, 10, 0. Should always check my arithmetic as we're going along. The second one, let's see, when we do row 3, I mean, we get 0, what, negative 10, and a 5. Sure, I'm going to go back and divide that by, of course that's the way they set it up, that's all right. And then negative 10, 0, 10. Did I do those right? All right. So what's the next step now?
Probably swap rows 2 and 3.
Okay, why do we want to swap rows 2 and 3?
So you can hit it in the second row.
Okay. Right. Notice that the way it's set up right now, I can't get a pivot in second column, right? We agree? Okay. Views that they, well, it was set up, I multiply by 10 so that I can get rid of the fractions, and then what am I going to have to do here to get a pivot in that row? Oh, I'm going to divide by 10. Actually, I need to divide by negative 10, but thought I was being clever getting rid of the fractions. I really didn't want to deal with them, though, because I didn't want to deal with the fraction arithmetic in my head. All right, so next step is to do what then? Good, yeah, take 1/10 of row 2, negative 1/10 of row 2 and replace row 2. So rows 1 and 3 stay the same, and row 2 is going to become 0, 1, negative a half, 1, 0, negative 1. Good news is with these is that we can check our answer when we're done. How are we going to check our answer when we're done, by the way? Calculator? That too. If I get the inverse at the end, what should I be able to do? Multiply by the original and see that you get the identity, right? Or calculate. All right, what's the next step?
Getting rid of the 0 above the 1 in the second column.
So,
Or just multiply row 2 by negative 1, add it to row 1.
okay. So that doesn't change row 3 at all, because row 3 is not even involved. It also doesn't change row 2 at all. It does change row 1, because that was kind of the point. Negative of negative a half, so I get 1/2 plus negative 2. So I get negative 3 halves. Negative a half plus 5 gives me positive 9 halves. And then I get 1 up here.
Where'd you get the negative half plus 5?
Oh, thank you. That's a 1. Thank you. That's just a 4. Thank you. I was thinking about the previous column. This is why I said check my answer. This is why I'm encouraging you to use the row operations on your calculator. It's really, 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 really easy to make a small arithmetic mistake in these. All right. Next step. Are we okay with this step so far? Next step.
You have to get zeros above the. Well, would you get the 5 to a 1?
I would do that first, yeah. So what do you want to do? Okay. Yep, you're right. So that leaves row 1 and row 2 the same. And then makes the third row 0, 0, 1, negative 2, 2, 0. And on the last couple of steps, what do we need to do? Okay. Good. So the 3 halves, row 3 plus 1, row 1, replace row 1. And 1 half, row 3 plus row 2, replace row 2. That keeps row 3 the same. And these two columns are going to be the same. And then we're going to get zeros here. So this, when you get towards the end of the row reduction, at least the left-hand side, the calculations are pretty straightforward because it's the whole point of why you're doing it, right? All right, 1 half times negative 2, or sorry, let's do the 3 halves. 3 halves times negative 2 is negative 3 added to 4 gives me 1. 3 halves times 2 is 3 added to the 0 gives me 3, and then I'll get a 1 up in the upper right. 1 half times negative 2 is negative 1 added to the 1 gives me 0. And then 1 half times the 2 gives me 1, added to the 0 gives me 1, and then I'll get a negative 1 here. That's doing anything with the 0 is not doing anything. So what that tells me is that if I look at the original matrix, so the original matrix is, remember again, 1/5, 1/5, negative 2/5, 1/5, 1/5, 1/10, and 1/5, negative 4/5, 1/10. The inverse of that matrix should be what? So I'm just using the superscripted negative 1 to denote the inverse. The inverse of that matrix should be what? Okay, so the 1, 3, what we ended up on the right-hand side there. So the 1, 3, 1, 0, 1, negative 1, negative 2, 2, 0.
Negative 1 in the top right corner.
Oh, yep, it's just the 1, thanks. Now we should be able to check, right? If you take this matrix without the negative 1 power on it, but this matrix and multiply by that one, we should get the identity. So we notice that we take 1/5 times 1 plus 1/5 times 0 plus negative 2/5 times 2, negative 2. You do get a 5th plus 4/5, which gives you 1. Right? If I take a 5th times 3, that's 3/5. A 5th times 1, so that makes me 4/5, and then I'll get a negative 4/5. I really do get 0. And then when I take this row times that column, I'll get exactly canceling out the 1/5, right? It's got a 1 and a negative 1. Right? And you can check the other one to make sure that you get what you're supposed to get. Let's just check the middle one here. The one that should be right directly in the center.
1/5 times 3 is 3/5. 1/5 times 1 is 1/5, so you get 4/5 plus a fifth. So you get 5/5. Then you get 1. So if you go through and check it, you should get exactly what you would expect. Questions on that one at all? Is the process okay? It's tedious, certainly. This is why after we get through this chapter, I'm not going to expect you to be doing all these by hand every time. Okay. That's what the calculator is for. All right, well, let's talk about a little bit more with stuff in section 1.6. We've been kind of doing them both together. The main result for number 6 was showing, or 1.6 was the long-winded theorem that we did last time. But part of that is was the idea that if you've got an invertible matrix, then it doesn't matter what you put on the right-hand side for your matrix equation, you can always solve it, right? Because you always multiply both sides by a inverse. So some of the questions that you see in the homework after this section ask you things like, looking at, say, number 18. This is on page 67. So the system is x1 minus 2x2 minus x3 equals b1, negative 4x1 plus 5x2 plus 2x3 equals b2, and negative 4x1 plus 7x2 plus 4x3 equals b3. And the problem asks you to find conditions on the b1, b2, and b3 so that the system is consistent. All right. So if we write this in matrix form, if the matrix has an inverse, so if we write this in matrix form, and the first row is what? 1, negative 2, negative 1. Second row would be negative 4, 5, 2, so on down the line. If this matrix is invertible, does it matter what we put on B1, B2, B3? No. We already know that, right? If the coefficient matrix for the system is invertible, then there aren't any conditions that we have to worry about for the B1, B2, B3. Okay? So the issue becomes what happens when it's not invertible. So this is one where we're going to need to do row reduction and see what we can find out what has to happen with the B's. All right, so we'll set up our augmented system, our augmented matrix, I mean. And we're going to row reduce like before. Now, I'm going to be a little bit lazy. I'm not going to do the complete Gauss-Jordan reduction, meaning I'm not going to worry about getting zeros above the diagonal here. I'm only going to worry about zeros below. Okay? Because if I see pivot here, pivot here, pivot here, I already know it's invertible. Right? Because if I can get a pivot here, I can definitely get zeros down here, right? If I can get a pivot here, I can definitely get zeros both here and here, right? And if I get a pivot here, I can definitely get zeros here. So if I see pivot, 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 I know it's invertible, and I can say that there aren't any restrictions on the B's. It can be whatever you want, because the matrix will be invertible. If I get down here and I have a row of zeros, then I can't go work backward anyway off of here. And so it's going to be this last entry down there that's going to tell me what needs to happen with the B's. So I'm only going to do Gaussian elimination rather than the whole Gauss-Jordan. Right? I'm just going to work below the diagonal, not above and below the diagonal.
I don't need to for this to answer this question. Okay? So, still starts off with I need a 1 in the upper left-hand corner. Ta-da! It's there, right? Okay. What do we need to do next? We need zeros below it, right? So what do we need to do to get zeros below it?
4 times row 1 plus row 2 plus row 2.
Okay. And same thing for row 3, right? Doesn't change row 1 at all, but we do change the other two. 4 times negative 2 is negative 8, plus 5 gives me negative 3. 4 times negative 1, negative 4, plus 2 is negative 2. Leave a little bit more room over here. Because over here I don't know what B1 is, right? So the best I can write is 4B1 plus B2. That's all I can write. Likewise, 4 times negative 2 is negative 8 plus 7 gives me 1.
Maybe negative 1.
Negative 1. Thank you. 4 times negative 1 gives me negative 4 plus 4 gives me 0. And then the 4 times the B1 plus the B3 is just 4B1 plus B3. So far, so good? I say we're actually done at this point, and we can tell there are no restrictions. And let's see why. I take this, say I swap these two rows. So pretend like for right now that this is in row 2. Okay? When I make this a 0, am I going to affect this at all? No, because there's a 0 here, right? So if I move this up to row 2, I'm going to get a pivot in column 3. So I'm going to see pivot, pivot, pivot. Right? So at this point, I can tell by looking that this is going to be row equivalent to the identity matrix, the coefficient matrix is, ignoring the last column. Okay? So if we continue, this part is row equivalent to the identity matrix. Everybody see what I'm saying with that, by the way? If I flip row 2 and row 3, I get the pivot that I want in row 2. And by getting the 0 below it, I'm not going to change what's in column 3 at all, because there's a 0 there. So this is row equivalent to the identity matrix, which means that the coefficient matrix is invertible, which means that there are no restrictions on the B's. It doesn't matter, what I mean by that is it doesn't matter what B1, B2, and B3 are, we can always solve it. Now again, this one was a special case. This was a special case because I was able to get a 0 here and a 1 here, right? Pretty quickly. Which meant that I could see that I'd get a pivot in column 2 and a pivot in columm 3, because I wouldn't be able to kill this one, right? Now, had this been, let's ask it this way. Let's say instead of having this be a 2, let's say we change it slightly and make this a 1 instead. What if we would have had the original system be x1 minus 2x2 minus x3 equals b1, negative 4x1 minus 5x2 plus x3. Oops. I want to be 4x3 equals b2, and then negative 4x1 plus 7x 2 plus 4x3 equals b3.
In the second row, you have plus 5x.
Oh, plus 5x2, thank you. Okay, so all I'm doing is just changing that coefficient on the x3 from a 2 to a 4 in the second equation. That's all I meant to do. I threw a negative sign in there instead as well. But so going back up to the original here, if I take this out, take out the 2, and make it a 4 instead, what's it going to make this term equal to? It'll be able to 0, right? So this will turn out to be a 0 here. If I take it out. Okay. So now, notice that I'm not, the same idea here, I'm not going to be able to get a pivot in that last column, correct? It's not going to be possible, because if I get rid of this entry, I'm still going to have a row of zeros. So to finish that off, let's say we swap row 2 and row 3. So I've got 1, -2, 1, B1, 0. I'm going to go ahead and do the negative row 2 after I do that, just to save some space. 0, 1, 0, -4, B1, minus B3. I did 2 steps at once. Just so I didn't have to rewrite the matrix again, just flip the negative signs. So I swapped them, and then I multiply by -1 for row 2. After I swapped. It doesn't matter if you do it before or after, I just did it after. Okay. All right, so now we want to get a 0 below the 1. What do I need to do to get a 0 below the 1? Good. Good. Oops. All right, so then we get 0, 0, 0 here, don't we? And then if we take 3 times this and add it to this, the interesting part is this part. We get -12b1 plus 4b1. So we get -8b1. I get a plus b2 and a minus 3b3. If I did my arithmetic right. All right, so remember what the original question was. A lot of arithmetic. I might have forgotten what the original question was. What was the original question?
What values for B? Is it consistent?
Good. It said find conditions on the B's so that this system is consistent, right? This system actually has a solution. That's what consistent means, correct? So what has to be true in order for this system to be consistent? What has to be true in order for this system to have solutions? Yeah, Megan.
Doesn't the last row, like, if it's zeros, then the other side has to be zero?
Cool. Good. That's right. So what has to be true then in order for it?
All of the things have to be zero.
No, they all have to be 0. I mean, that's one.
Well, then you just have to add together.
Yeah, exactly. So if I take this term, this entry has to be 0, right? So in order for this to be consistent, we need the -8b1 plus b2 minus 3b3 to be 0. Or if you liked it to look a little bit better, I could solve this for, say, b2. The only reason why I wrote it this way was essentially that makes it look like I can pick whatever I want for b1 and b3. But then if I pick whatever I want for b1 and b3, then b2 has to be that. Right, so if you pick 1s for b1 and b3, then b2 has to be 11 in order for it to be consistent. Does that make sense? So that's how you would attack this particular type of problem. You just go through the row reduction. If you see that you're going to get the identity matrix on the left-hand side, then you know it's consistent no matter what, because the matrix is invertible.
If you see a row of zeros pop up, like it did here, then you know that you need a 0 here and just state that's the conditions that you need. In this case, it's really condition that you need, right? But notice basically what it says is, and this is stuff that we're going to come back to later this semester, basically what this says is, I've got choices I can make. I can make 2 choices, but I can't make a third, right? It's not consistent all of the time, but I do kind of have 2 choices that I get to make. But once I make 2 of the choices, the third one is determined for me in order to be consistent. And it's not unlike when you graph a function, right? You pick an x, you get the y, right? You don't get to pick the y too. You can pick whatever x you want, but once you pick the x, the y is determined for you. Or in 3 dimensions, if you have a function of 2 variables, you get to pick the x, you get to pick the y, but then the z is determined for you. So what we're saying in here is that one of the b's depends on the other 2. Does that make sense? All right. Given the fact that we only have 3 minutes, let's go ahead and stop there. I posted a review this morning for the exam. We got the exam Friday. I've got the room reserved for 8, so that you can come in at 8 to start early. If you have class at 8, I know a couple of you have class at 8, just schedule a time with me separate so that we can get you a couple of hours to have time to take it. Mainly I just want to make sure you have time to finish it. That's why I'm doing that. All right? All right, have a good one. We'll see you on Wednesday.